Hello and welcome to our presentation for the Ford Additive Manufacturing Capstone Design Project. Our team consists of Edward, Omid, myself, Elizabeth, and Anil. Our UCI advisor is Ben, and our Ford sponsor is Sid. To provide a bit of a background, low volume production can be expensive when using injection molding, but additive manufacturing can provide ways to reduce costs. In our case, we will be using a multi-jet fusion 3D printer to take advantage of its ability to nest parts. We have been asked to redesign an automotive air duct for AM economics, and to drive down part costs, we will take advantage of DFAM principles to develop multiple designs that maximize the nesting efficiency.
So we came up with a design requirements table based on the objectives set out in the problem statement. We had 5 requirements going from withstanding estimated temperature range within the vehicle, being within a percent pressure drop of the current design, being able to maximize the number of parts per batch in order to minimize the unit cost, and being sure that it fits within the local assembly with no interference. Secondly, we used the Pugue matrix in order to proceed with our designs. We had a list of conceptual designs that we came up, and we needed a way to proceed and choose the concepts to move forward with. And we did that using a Pugue matrix that scored each design and gave it a relative score based on criteria that we got from our design requirements.
For our prototyping process, we printed several iterations of specific design features, such as the snap fits and the hinge for the book style shown on this slide. By doing this, it allowed us to determine the best tolerances to use that had a snug fit for the snap fits and the minimum distance between each part to allow movement for the hinge. Once that was figured out, it allowed us to easily integrate it into a whole CAD model for the air duct. And one additional feature we included is that we drafted the walls outward to prompt nesting efficiency when printing.
On the top left, you can see our initial telescoping design. We used tapered cylinders that used friction to stay together once extended. On the right side, you can see our revised design, which uses a bead locking mechanism that gives a more secure fit. Also, the telescoping feature is triangular to fit better with the local assembly. On the bottom is our separated wall design. We planned on using snap fits to secure the individual pieces together, but after discussion, we decided to incorporate hinges in order to reduce the post-processing time.
Here we have the nesting scenarios for the following duct designs: snap fits, book style, and telescoping. We compare the number of sets that can fit in one build with a 5mm and 2.5mm part interval. With a smaller part interval, we are able to nest more parts in one build. For example, with a 5mm interval for snap fits, we have a total of 50 sets, but with a 2.5mm interval, we are able to get a total of 96 sets.
One of our goals was to determine business opportunities using additive manufacturing versus traditional injection molding production. Using the nesting scenarios, we were able to find the price per unit for each design. On the figure on the right shows certain points at low volume production where each design can be utilized over injection molding.
To analyze pressure drop across our ducts, we used ANSYS CFD simulations. First, we analyzed the original Ford duct and found a pressure loss of about 25 pascals, and we confirmed this value with hand calculations. On the bottom, you can see an example of one of our designs and that it has a 35 pascal pressure drop.
We chose to conduct 2 print jobs testing our prototypes. And on the first print job, we used our locking mechanisms for the various duct designs in order to test the functionality. And once we confirmed the functionality, we went ahead and conducted a second print job that printed the whole duct with the locking mechanisms embedded. Thank you for watching the presentation. We hope you enjoyed it, and feel free to reach out to us if you have any questions.